Okay. Can everybody hear me? Yes. Usually I have a quite loud voice. But anyways, I first would like to tell you a few words about myself, where I came from or where I come from, before I start with the lecture. So I actually was born in Berlin, in Germany, at that time in West Germany. I did my PhD at the University of Karlsruhe, and nowadays it's not called the University of Karlsruhe anymore, it's called now the KIT, seems to be more popular, so the Karlsruhe Institute of Technology. I spent a few months at the Fraunhofer Institute in Freiburg, which is in the south of Germany. Then I've been roughly 4 years at, well, almost 4 years at Northwestern University with Professor Ted Belichko. And I returned to Munich, Technical University of Munich, roughly 1.5 years before I have been appointed as senior lecturer in a very beautiful country in New Zealand. It's much nicer than Germany. But nevertheless, in 2009, I returned to Germany, and there I'm now a full professor at Bauhaus University, Weimar. So that shows here the map of Germany, just to give you an idea where Weimar is located. So this is here the state of Thüringen, and that here is Weimar, this very small point. We have roughly 65,000 inhabitants, so it's a quite small city. We have only 4,000 students at the university, and only 4 faculties. That is Weimar downtown. So you can see it is also quite small. That is here the tourist information. And Weimar is actually, maybe somebody of you have heard the Weimar Republic. That was the time between World War I and World War II. Of course, the government was not in Weimar. It was just proclaimed there because of the riots after World War I. But maybe you also know some famous poets, they lived in Weimar. So the 2 most famous ones are Goethe and Schiller. So that is their statue in front of the National Monument. And we have also a lot of small castles, like that one. That is Castle Belvedere in the south of Weimar. And I would say that is our castle. That's the Institute of Structural Mechanics. And what you see there, that is my office. So that's the window where I usually I don't look out, but that's where I could look out of the window when I'm there. So I want to give you like an outline what I want to talk today. So I have wanted to present some state-of-the-art computational methods for fracture. I will start with a brief motivation. Actually, that is a quite challenging outline. So my key focus will actually be on this part of partition of unity enriched methods. And when I say partition of unity enriched methods, I mean the extended finite element method. I also will give you a historic overview of how fracture was modeled in meshfree methods. And in fact, some of the concepts have been also adopted in XFEM. The last 3 topics, I'm not so sure if I will cover all of them, but at least I would give a brief idea of what they are. So peridynamics is a method that was developed in 2000 by Silling and was particularly developed for dynamic fracture, so when you have a lot of cracks. What is also relatively popular in recent years is are phase field methods for fracture. In fact, phase field methods are used in physics for a long time. And also the approach is actually not that new. It has been proposed by Bourdon in 1998, and I think even before there's a book about variational methods of fracture. But I think really popular was this approach by Christian Mier, who I think published it around 2009. I also would like to talk relatively briefly about so-called multi-scale methods of fracture that in my opinion have actually a different application than all the other methods. So I know you have had a very nice presentation and lecture in the morning, so you know a lot of things about fracture mechanics, and probably most of you had that knowledge also before. Nevertheless, a brief introduction. So what we would like to model is material failure or structural failure. So we would like to know if a structure or if a material fails, and the progenitors of material failure are usually cracks or sometimes also shear bands. So the cracks initiate, propagate, maybe they branch, they join, and finally that causes a fracture of the structure. So when you want to model that in a computational analysis, the key question is what problems occur. I'm going to talk about this in a moment. how can these problems be avoided? And is it really necessary to model a crack explicitly? So they are a different type of approaches. I would say they are discrete fracture models. That's what I'm going to talk about today. But they are also like continuous approaches to fracture. So actually, the phase field approach is not really a discrete approach to fracture. That's a continuous approach to fracture. I believe, and I think a lot of my colleagues also believe, that for many problems it's indeed necessary to model the crack explicitly. And that will lead us now to the next question: how can we model a crack? And therefore we need two ingredients. We first need a method that can capture the crack kinematics, which is a jump in the displacement field. And then we need the physical condition in order to decide if a crack initiates or propagates. We need to determine the length of the crack, and so on and so forth. And I'm going to focus in my presentation only on the first aspects. I look at methods that can capture the crack kinematics, the jump in the displacement field, though of course it's very important to also look at the second ingredient. I think it's maybe even more important, and that is closely related to the constitutive model. So in the morning you focused on linear elastic fracture mechanics, or also some extensions to elastoplastic fracture mechanics. You can of course have also like a continuum point of view on this topic, and I will show like one slide to that a little bit later. So back to what are actually the problems that occur when you have fracture. I focus now mainly on nonlinear materials. I know my picture is here not the nicest one, but that is here a classical stress-strain curve for a quasi-brittle material. So with increasing strains, we have decreasing stresses. So on that domain is called strain softening. So apparently we use uniqueness of the solution we have for two different values of the strain, the same value of the stress. The solution is no longer stable, and that means that our boundary value problem on dynamics, the initial boundary value problem, is ill-posed. And if you model such an ill-posed problem with, for example, finite elements, that will lead to mesh-dependent results and a so-called localization on a set of measure 0. So how does such a mesh dependence manifest? It manifests in different ways, but I would like to point out the load deflection curve. So for example, if the energy which is dissipated at post-localization is not negligible anymore, then you would have a load deflection curve that does not converge when you refine the mesh. So your results are actually physically meaningless. And what one can do is one can use a regularization to restore the well-posedness of the boundary value problem. And there are many approaches. I want to focus here only on 3 of them, on gradient models, nonlocal models, and viscose models. This is actually a continuous approach to fracture. All these methods have certain advantages and certain drawbacks. I would like to focus only on the last line of the drawbacks that all of these 4 methods have. Of course, if you consider that as a drawback. So what they do is they introduce an intrinsic length scale. They smear the crack over a certain width, and that requires a relatively fine mesh to resolve the crack over the width. So we need a lot of degrees of freedom. And secondly, they are not able to capture the appropriate crack kinematics, which is a jump in the displacement field. So what can be done? One can use so-called cohesive zone models, and I think in the course of the conference next week, there are also a lot of contribution about cohesive zone models, and I would like to give you like a brief idea what a cohesive zone model is. It was originally introduced by Barenblatt in 1962, and he actually developed it for crack propagation along existing grain boundaries. Hillerborg extended that concept a little bit later and allowed the crack to propagate arbitrarily through a domain. And the principal idea of this cohesive zone models is shown here in that figure. We have at the beginning a constitutive model with strain softening. We have a cracking criteria, and when that cracking criteria is met, one switches from a continuum to a discontinuum. We introduce crack surface and external boundary. And to ensure that the right amount of energy is dissipated at post-localization, we have here a so-called traction separation model, which I illustrate here only in 1D for pure mode 1 fracture when the crack opens. So that is here the traction, and that is here the crack mouth opening. So usually we have also different cohesive zone models. That is here a rigid cohesive zone model. So we have here the maximum stress at the crack tip here, and then it decays down to 0 until the crack is widely open. So in the governing equation, so for example, we look here at our linear momentum equation. Of course, when we have statics and the inertia term would vanish, we have now an additional term due to the cohesive zone model, and that is basically highlighted here. So we have here the cohesive traction, and they are usually formulated in terms of the jump and the displacement field. And I'm going to talk now mainly about how to introduce this jump in the displacement field. So when we would like to model fracture, the first bad news is that we don't have one general method that can handle all type of fractures. And what do I mean with that? Let's look, for example, at an impact, like here, impact into glass. You can see we have here a huge amount of fragments, a huge amount of cracks. They coalesce, they branch and join, and so on. And a method that can deal with a single crack, for example, XFEM, might not be very well suited to deal with this type of problems. On the other hand, if we have few cracks here, then a method like XFEM is probably very well suited. This are like here some other examples. For example, this is here also a very famous accident that happens here in the US during a flight where the entire roof was ripped off. Okay, I want to start now with the first part of the lecture, mesh-free methods, and in fact I would like to focus on how to incorporate cracks and mesh-free methods, but I don't know who of you is familiar actually with mesh-free methods. Is anybody working on meshless methods? So in fact, I said no meshless and mesh-free methods, in fact they are the same, it's just like a different notation, but in the literature they either refer to mesh-free or meshless method, and I would like to give a brief introduction. I would like to have some definitions. I would like to show you also some differences between mesh-free methods and fine element methods. So first of all, to the similarities. So we are still here trying to solve a continuum mechanics problem. So our, for example, equilibrium equation. And the only difference between a mesh-free method and a fine element method is basically how we compute the shape function. So that is here a mesh-free approximation, UH of x. So we have here the sum of the shape functions, phi, and it's of the node j, and uj are the nodal parameters. Or of course, you can write it also in tensor notation by plotting u bold or using here this additional notation. So that figure should roughly illustrate the shape of the mesh-free and the fine element shape function for the node here in the middle. So that is here a classical bilinear shape function of a Q4 element. So you cannot see this bilinear term in the diagonal. And that shows here how roughly a mesh-free method or mesh-free shape function looks like. So we have here a central point in the middle. So when we look now from the bird perspective, from the top, that would be, for example, this yellow point. We have then a so-called domain of influence. In this domain of influence, phi is unequal to 0. So that means that is a set of functions S. Outside the domain, the shape function is equal to 0. That means all these particles here in black and also the red, purple, and green one will contribute to this summation. So you can see we have also now a parameter we can play with. We can make this size of the domain of influence, the so-called support size, larger and smaller. You can consider this as a positive effect. We have now more flexibility. In reality, it's quite difficult to calibrate now the size of the domain of influence, and the results will be quite sensitive to the size of the domain of influence. So I want to give another definition, a so-called partition of unity. What does it mean? It's very simple. It simply says sum of the shape function is equal to 1. So if we look here at the linear finite element discretization, of course, finite element method is also a partition of unity method. So we can, for example, compute the shape function of this point. So we have the shape function of this node here. We have the value of the shape function of that node, and it's supposed to be equal to 1. This property is also fulfilled by a mesh-free method. So I have not actually said anything about a mesh-free method, but that shows a mesh-free shape function. So you can see when I sum up the shape function here in this domain, it's also equal to 1. but you can see some subtle difference. So you can see, for example, if we look here at the position 2, that's a shape function of the node at this position. It does not fulfill the so-called Kronecker delta property. That means the shape function of node j at the position xi is unequal to the Kronecker delta. So that means a meshfree method is not, or many meshfree methods, it's not a true interpolation. It's only an approximation. It does not go through the data. So since the shape function at this node is not equal to 1, of course you can see that's maybe the neighboring node here. It's also not equal to 0. The physical value, the displacement at the position x1 is not equal to the nodal parameter. And that complicates the imposition of the essential boundary conditions. So finite elements, you solve usually the system, at least for linear elasticity, k times d equal to f. So you get the nodal parameters d. They are equal to these physical values. But in meshfree method, they are not. After you obtain the nodal parameters, you have to interpolate with your meshfree approximation to get the displacement at this position. So and that shows here now a linear finite element shape functions, this classical head shape functions. You can see we have here jumps at the element edges. First derivatives and second derivatives are not defined. We have here the Dirac delta functions. On the other hand, if we have now a linear meshfree approximation, that means we can reproduce a linear function exactly. The meshfree shape function looks a little bit like this. So it's also continuous. It's actually here, in this case, C2 continuous. What does it mean? C2 means it's 2 times, the approximation is 2 times continuous differentiable. So you can see that here that's the second derivative. The third one would be not continuous anymore. I also would like to point out we have here only linear completeness. We can only reproduce a linear function exactly. So maybe some of you have heard about isogeometric analysis. Isogeometrical analysis, the shape function NURBS, they are mostly also higher order continuous, unless you have like knot insertions or you have different patches. But of course you need to have higher order shape functions, like quadratic shape functions, to have that property. In fact, the linear IGA shape function is equivalent to a linear Lagrange polynomial. So I would like to come to the next point, the so-called kernel function. That is an important ingredient to construct a certain meshless method. So any kernel function can be actually implemented into a meshless approximation. There are usually certain requirements on this kernel function. So the kernel function is W. So R is the distance between 2 points. So we have like a node xi and then the neighboring node xj. And H is the size of the domain of influence, for which the shape function is supposed to be equal to 0, and related also the kernel functions supposed to be unequal to 0. So that is here like a theoretical requirement. So when we shrink the size of the domain of influence to 0, we should obtain the Dirac delta function. If we integrate the kernel function over the domain, we should obtain equal to 1. That looks a bit like partition of unity. We would like to have compact support. That means the kernel function is equal to 0 after a certain domain of influence size is exceeded. That is actually not necessary. There are also some methods which have global support, but of course that makes a method computationally expensive. And usually one requires that the kernel function is symmetric and the first spatial derivatives is skew symmetric. Instead of expressing now the kernel function in terms of the distance between the particles, one normalizes it by dividing it by the size of the domain of influence. So that is one classical kernel function. There are also other words for the term kernel functions, like weighting function or window function. That's a quartic B-spline. So the quartic B-spline is, if I remember correctly, C2 continuous. So when Z is between 0 and 1, we have a Z form, and otherwise it's equal to 0. So here again, R is the distance between 2 points, and H is the size of the domain of influence. So that shows here the kernel function of the quartic spline. So that is here in 2D. That is here x direction, y direction, and here that is the value of the quartic B-spline, and that's the first derivative. I would point out already something which is, causes some difficulties in meshless methods. that the derivative of the quartic spline is equal to 0 at the point itself. So that is usually not the case in finite elements, but here that is equal to 0, and that causes some difficulties. I also mentioned we can adjust now the size of the domain of influence of this kernel function. So here we have h over x. So of course I can say, for example, we have now only one neighboring node, so h is equal to x. And let's see how we can reproduce a given function. So that is somehow arbitrary, but let's assume we have the function 1 minus x squared. That here is an analytical solution. And we look now how our mesh-free approximation can interpolate or approximate this analytical solution. So you can see it does actually quite poorly. We have here this high frequency oscillations. And when we increase now the size of the domain of influence, let's look, for example, at that node. Let's keep two neighbors from the left and from the right. Then you can see we do much better. So that is an approximation which is linear complete. So we don't actually expect that we exactly can reproduce an analytical solution. But you can also see if I further increase the size of the domain of influence, for example, including 4 particles in the sum from each side, then we have this excessive smoothing. So our results actually get worse instead of better. So that, of course, depends also on the regularity of the problem. So, for example, if we have a shear band, we know we have a high gradient, and it's probably better to have a small domain of influence. While when we have a smooth solution, we might want to have a larger domain of influence. And calibrating the size of the domain of influence is still an open issue in meshless methods. So I would like to show you the elementary Galerkin method that was proposed in 1994 by Ted Pelichko. I think meanwhile there are some more advanced meshless methods, but I think it's an extremely popular method, and I would like to explain you the basic idea. It looks in a way a little bit similar how we actually derive the shape functions of a linear triangle directly in the physical space. So of course we can use also an isoparametric mapping, but this linear triangle is often formulated directly in the physical space. So we have here a movingly square approximation. So that is here our u of h. That is p is a polynomial function. So usually we have here polynomial functions in there like 1, x, y, z, x squared, and so on. Depends of what function we would like to reproduce. And for Galerkin method, we need at least linear completeness. And a here are unknown parameters, and in a movingly square approach, they depend also on x. So now, of course, there's a difference to how we derive the linear triangle in FEM. So we define now a discrete weighted L2 norm J that depends on the unknowns A. So we have here PA minus U of, actually that's not correct, it should be UJ. So I have actually a few mistakes here in my slides. I apologize for that, but I will point that out also when I go through the slides. So UJ, these are the nodal parameters. And W, that is here our kernel function. N here is the number of nodes in the entire discretization, and our index M here is the number of functions in this vector P. So for example, if we can reproduce in 2D the polynomial 1, x, and y, that would be a 1 times 3 and a 1 times 3, and here a 3 times 1 matrix. So of course we can recast that also in a vector matrix form. We store now all these vectors in P. That would be an n times m matrix, m times 1 and n times 1 matrix. That is here a diagonal matrix of n times n, and here PA minus U. So we minimize finally this discrete weighted L2 norm with respect to A. Then we obtain that equation here. We solve this equation with respect to A. And then we plug A back into the approximation above there. And then we have constructed the shape function of an elementary Galerkin method. So here again you can see we have here P transpose W. That is also not correct, should be P. And that is in the literature often the matrix A, which is of M times M. So one can see when we have now more functions in this polynomial basis, we have a much larger matrix. P transpose W, that is basically a matrix which is called often B. And U of x hat, this is a nodal vector that contains all the nodal parameters. I also would like to point out that is P of x hat, so that is of course like a matrix that contains discrete values. This matrix P does not depend on x. The same U of x hat, that also is a vector of nodal parameters. It does not depend on x. Only A and W here depends on x. So now plugging A back into the approximation here. Oops, that was not good. Okay. Leads finally to UH is equal P transpose. That is here the first time, and then we have to invert this matrix A minus 1 B times U of x hat. So P transpose A minus 1 B, this is our EFG shape function. Or you can write it also in this summation. So we sum here from J equal to 1, K equal to 1 to M, and I equal 1 to N. So in summary, we have here a basic approximation, P transpose A, so that is also not correct, it should be vice versa, P transpose A. We minimize this quadratic form with respect to our unknown parameters A, solve this equation with respect to A, plug it back into the basic approximation, and then we have the classical form you know also from finite elements. Sum of the shape functions times nodal parameters. So, and that is the way how we compute the shape functions. There are certain issues in finite in meshless methods. I focus here now on the elementary Galerkin methods. One is integration. So we don't have here a polynomial function. We have actually a rational function. So integration is not exact when we use Gauss quadrature. And in fact, if we use higher order elements, it's also not exact because we have still the Jacobian, right? So even when you have like Q4 elements, you integrate actually a rational function and not a polynomial. But there are also other ways to integrate in meshless methods. So classical way is nodal integration. So you have here the integral of f over domain d omega. So one can construct a Delaunay triangulation, and then the Voronoi cells and the volume of this Voronoi cells will serve as quadrature weights here. And nodal integration leads to an instability. It's similar to an instability due to rank deficiency in finite elements. And one issue is that most of the time, for example, you have to actually integrate the derivative of a function, B transpose C, B, d omega, for example. So in the derivative, that's what I mentioned before, at the node itself is equal to 0, and that is suboptimal. And there are ways to stabilize that. One way to stabilize is a so-called stabilized conforming nodal integration that was first introduced by J.S. Chen in 2001. And it was later on also used in the so-called smooth finite element method by G.R. Liu. I come back to that a little bit later. It has actually two ingredients. First of all, and sometimes I wonder why that actually works, because we don't work anymore with a compatible strain tensor. We use a so-called smooth strain tensor. So here's another mistake. So it shouldn't be epsilon tilde, it should be epsilon. That is 1/2, then in brackets, nabla u plus u nabla. And then we multiply this with a smoothing function and integrate it over the domain. So that is a so-called smooth domain. Omega 0 is a smoothing domain, and that is here a smoothing function that should fulfill two key requirements. First of all, it's supposed to be larger or equal to 0. So of course, when you have like a positive strain, you would like that it remains positive. So tension remains tension. And if we integrate now this function over the domain, we should obtain a value equal to 1. And the easiest way to construct now such a function that fulfills these two requirements is simply to use the area of that smoothing domain. And that is denoted by AM. So we choose now a function 1 over AM, and then apparently we fulfill these two requirements. Otherwise, this function psi is equal to 0. So the second ingredient is we use now the Gauss divergence theorem. Actually, we use the Green theorem to transform the domain integral back into a boundary integral. So we have here the compatible strain tensor 1/2, then AM, that is constant. We can take it out of the integral, and then we transform this domain integral back to a boundary integral. And the key feature is we don't have the derivatives of u anymore, and n is a normal to that so-called smoothing cell. And you can see we integrate now along the boundary of that smoothing cell. That would be our Voronoi cell. And at that domain, first of all, we need only the shape function itself, but they are not equal to 0 anymore. Another way is to use so-called stress point integration. So we simply add stress points that will also stabilize nodal integration. I think I don't want to go in too much detail and come relatively soon also to fracture, actually. And another way is to use cell integration. And Atluri, actually, he introduced the notion of truly meshless method. So apparently now our method requires a background mesh for integration. So what we would do, we would construct here now a background finite element mesh. I think it's very hot here. What we would do, we construct here a finite element background mesh, and then we would integrate over this finite element background mesh. So of course we don't necessarily need to align the meshfree nodes, which are here illustrated in black, to the finite element nodes. We could have also such a discretization. So we have, for example, a structured background mesh, and here an arbitrary discretization cannot be that arbitrary because we still need a few nodes inside a background mesh. And then we have a classical isoparametric concept. So we integrate then here by mapping from a parameter space back to a physical space using Gauss quadrature. So in fact, to be here correct, we should have here sum j, for example, here sum over I, and then we have here the quadrature weight wj times wi, actually. And then should be the psi I and eta j. Yeah. So here, as I mentioned before, this Gauss quadrature, we need n quadrature points to be able to reproduce or integrate exactly a polynomial of order 2n minus 1. And keep in mind, meshfree shape functions are not polynomials, so what is standardly done, one increases the number of quadrature points, but there are also smarter ways to integrate. Another issue is the imposition of essential boundary conditions, because this Kronecker delta property is not fulfilled. And one way to impose essential boundary conditions is, for example, Lagrange multiplier method. One can use also Nietzsche's method that does not require introducing additional degrees of freedom. And we don't have the problem to show that we fulfill the inf-loop condition. But I want to briefly show you how to impose essential boundary conditions with Lagrange multipliers. Actually, sometimes I review some papers where they show like very poor convergence rate with meshless methods, and from my experience, that is often related to the not very accurate imposition of these Dirichlet boundary conditions. So we have here the energy, so potential energy. Then we add now the energy for the Lagrange multipliers. So here G is the essential boundary conditions you would like to impose, so U minus U bar. So apparently U bar is now a constant value in this case. And lambda are the Lagrange multipliers. We can take now the first variation of this potential W bar. And I focus only now on the Lagrange multiplier energy here. So we have the first variation of the energy of the Lagrange multiplier. That is the first variation of lambda transpose. So that is like a attraction. And G is a displacement. So when I take the first variation of G, apparently that's only the first variation of the first term, because the second term U bar is constant. So I need to discretize and somehow on top of my displacement field and my test functions related to the displacement field, I need to discretize the Lagrange multipliers and the test functions. So, and here I'm also relatively free. I could, for example, use fine element shape functions, meshless shape functions, or if I would like to impose the Dirichlet boundary conditions in a strong form, I would use Dirac delta functions. Then I plug my discretization of the Lagrange multipliers, so lambda, delta lambda, and my discretization of U back into the weak form. I show only now the first term here. And then I end up with a discrete of equations K times U equal to F, and on top of it I have now G times the Lagrange multipliers equal to the gap. That is basically what I would like to impose. So I have here now my matrix G, that is the test functions of the Lagrange multipliers multiplied with the trial functions of the displacement field, and vice versa. That's why I have here G transpose. And of course I have the gap G, so there's nothing else but the integral of phi Lagrange multipliers times the imposed displacement. So I also like to show now an example of how to impose essential boundary conditions. So we have here symmetry conditions, Poisson ratio equal to 0.3, and I know the elasticity modulus is here not given, but we impose here now the Dirichlet boundary conditions, the constant displacement downwards of 0.2. That shows here now the discretization, and with also different discretizations of the Lagrange multiplier. So these small crosses, this is like the standard meshless nodes for the discretization of the displacement field, and the squares are related to the discretization of the Lagrange multipliers. So if we have to view, you can see of course here at the nodes it looks fairly okay. Yeah, this is of course exactly imposed, but not in between. If we have here more Lagrange multipliers, we have a more accurate imposition of the boundary conditions. But if we add too many Lagrange multipliers, we have here a singular matrix, and that is one of the issues of these Lagrange multipliers. Okay, now finally how do we model actually now cracks and mesh-free methods? Might be a bit counterintuitive. Meshless methods are higher order continuous. So what's now the point in trying to incorporate a crack there? However, meshless methods do not have this nodal connectivity like find elements. So what you would do in a standard find element method, you would align the crack boundary to your finite element mesh, and that requires remeshing. In fact, we are working also now on remeshing techniques because we believe due to the vast improvement of the mesh generators, it's actually not such a bad option to use remeshing. But before I come now to the issue, how do we incorporate cracks in meshless methods, I would like to tell you a little bit about the crack kinematics for a very simple example. So that's actually what we need to capture with our computational method. So let's assume we have here a bar, it's clamped on the left-hand side, and we pulled it on the right-hand side. So that is here the linear displacement field, the constant strain field when the bar is intact. And if we have, for example, a crack at a certain point, then we have a separation of the bar. So we show now the displacement field over the initial length of the bar. So apparently, since we have here two crack surfaces, we have here a jump in the displacement field. Excuse me. If you look at the axial strain, that is not defined here where the crack is, and of course in this case it should be the same, the strain on the left and on the right hand side. But of course, in generally it could be also different, depends on the application. So how do we incorporate these cracks in a meshless method? The first approach was the visibility method. It was proposed also in 1994 in the first elementary Galerkin paper. So in this case, the crack is considered to be opaque. And let's look, for example, at a particle A. Usually, in the absence of the crack, you could see we have here this radial basis functions, and when you look from the top, a circle, and all the nodes that fall inside that circle should contribute to the discretization and the summation. So what you do is you simply cut now the shape functions at the crack and exclude these two particles on the opposite side of the crack. And how will the shape function look like? It will look like illustrated here on the right-hand side. And you can clearly see here the shape function here is discontinuous. That will, of course, capture the discontinuous displacement field. But unfortunately, we have introduced also some artifact because the crack is supposed to end here. And the shape function is also discontinuous along that line. So and that, of course, depends on what point you look at. If you look now at the meshless point here, then for this point, he will see the crack like this. So we have here a kink towards the upper part. One way to circumvent this artificial discontinuity was proposed a little bit later by the so-called diffraction method. So what does the diffraction method do? It tries to eliminate this artificial discontinuity. So it's actually motivated like diffracts around the sharp corner. So the equations of the diffraction method, which I will not show here, do not have any similarities to the equations they use in optics. But The diffraction method makes sure that the shape function is still discontinuous along that line. That cannot be seen here very well, at least from that point of view. And it removes here this artificial discontinuity. A method that is a little bit simpler is a so-called transparency criterion, but let's say it's easier to implement. It assumes that the crack is transparent at the crack tip, and therefore it's also less accurate because the crack tip is also not at the position where it's supposed to be. So this figure looks a little bit similar to the one I've shown before. The approximation is actually quite different. I would also like to show you now an example, which is diffraction, transparency, and visibility method that shows here in a log-log scale the error and the energy norm versus ln h. So h is the distance in this case between the particles. For, of course, a structured discretization. So you can see the convergence rate as a visibility method is unaffected compared to the convergence rate of the diffraction and the transparency method. So the accuracy is slightly less. What you can also see, of course, that is a linear complete EFG approximation. So the optimal convergence rate should be equal to 1 for a smooth problem. And that is, of course, lost because of the singularity at the crack tip. When we look here now at the normalized stress intensity factor, so that is the optimal value of 1, unfortunately not in a log-log scale. So you can see also the visibility method is slightly worse than the diffraction and transparency method. That's for only a mode 1 fracture problem. So in order to improve the accuracy, one can use a so-called enrichment. I think you have heard about it a lot in the morning, so I don't need to say much about it right now. But what one can try to do, one can try to incorporate now the information of the analytical solution into the approximation. In fact, such type of approaches are also not very new. They have been pursued in the 1980s by Barsoom in the so-called singular elements. They have already designed special elements that can account for the analytical solution. And in 1997, Fleming and Belichko proposed also such an approach in meshless methods. And there are actually 3 types of enrichment schemes. One is a so-called intrinsic enrichment, and the other 2 are so-called extrinsic enrichments. So one can, of course, use the trigonometric identities that span the basis of the linear elastic fracture mechanic crack tip displacement field that is given here. And one can incorporate now this analytical solution into the meshless approximation. So the easiest way, or maybe not the easiest way, but one way to do it is you simply expand your polynomial basis. So you have the standard polynomial basis of your elementary Galerkin method, 1, x, and y. And now you introduce the solution from the linear elastic fracture mechanics, so square root of r sine theta over 2 and all the other 3 terms. And the MLS approximation remains untouched. So you still have the shape function phi. You have to invert this matrix A. The only difference is we have here now a different polynomial basis, which is not now polynomial anymore. And that is also why it's called intrinsic, because it's intrinsically introduced to the polynomial basis. Unfortunately, that has also some drawbacks. I mentioned we have to invert here this matrix A. And there are also some requirements on the inversion of the matrix A. So we need to have a sufficient number of neighboring points. We need to have at least the same number of neighboring points as functions in this vector P. And also the arrangement of points cannot be that arbitrary. However, we need actually this enrichment only in front of the crack tip. We don't need it far away. And if we simply omit now this enrichment far away from the crack tip, then we introduce an artificial discontinuity at the transition from the continuous to the discontinuous intrinsic basis. So what one tries to do to circumvent that problem, and this type of concepts are also used in other parts of computational mechanics, for example in multi-scale methods. I don't know, maybe you have heard about the Galerkin method or the bridging domain method that's actually based on a linear weighting of an energy. That is not a linear weighting of an energy, but the equations look actually quite similar. So what one would try to do is one introduces a so-called blending domain. So we have here like the crack, that is the crack tip. Then we would like to have an area where we use an enrichment. Of course, you have to define also this radius R1. And then far away, that is basically outside this outer radius, we would like to have an approximation with a linear complete basis of P that has only the functions 1, x, and y. And then we have this transition domain, or the so-called blending domain, that blends over the enriched domain to a linear domain. And that is done quite easily. We can now look at our displacement field UH of x. So we have now a function r times u enriched plus 1 minus r times u linear. So we need to choose now the function r, which is equal to 1 in this enriched domain. The function r is supposed to be equal to 0 in this outer domain. So that removes the first term. And it should blend over smoothly from 1 to 0 in this transition domain. So a very simple function that can be constructed is that function r, which is 1 minus xi. And xi is simply r minus r1 divided by r2 minus r1. So r is the radius, r1 is here the inner radius, and r2 is the outer radius. So that is apparently a function that blends over an enriched domain linear down to the linear approximation of the standard EFG approximation. Of course, one can choose also other functions of R. That is also a function that was proposed in the paper of 1997 from Fleming and Belichko. And finally, the only difference is we have here now the approximation U and the slightly modified basis functions phi bar, which accounts here for the enriched part in front of the crack tip and the linear part, which is farther away. So besides this, by the way, if you have questions also, then please feel free to just interrupt me and ask any questions. Okay, what one can also do is, theoretically, you don't need to use all these terms, which is of course more accurate, but if you would like to have like a smaller matrix A, so you don't need to invert, in this case, a 7 times 7, but only 4 times 4 matrix, you simply keep the first term of the enrichment, this theta over 2 makes sure you have a jump in the displacement field at the crack tip, and the square root of r ensures also the stress singularity. And some researchers also include only the square root of r term and use some other techniques to ensure the jump in the displacement field, like this, for example, visibility method. So another idea to improve the accuracy is the so-called extrinsic movingly square enrichment. So one would also introduce now the information from fracture mechanics into the discretization. So we have here P transpose A for the polynomial basis of the EFG approximation. And then we would introduce here now here this angular functions Qi and Qi1 and Qi2 related to mode 1 and mode 2 fracture. And K1K and K1 and K2K are approximations of the stress intensity factor. So these are like global parameters. So you would add now 2 additional degrees of freedom to your system of equations. You would solve for these degrees of freedom. You don't need to take derivatives with respect to them. So you can see they don't depend on x. And theoretically, you could use them also, as I said, as an approximation of your stress intensity factors without the need to implement the J integral or interaction integral. However, if you would use them as an approximation, they actually showed also that this approximation is quite rude and you cannot recover optimal convergence rates. So I show later on also some results, actually not with where we use here this as an estimate, but where you use the interaction integral to evaluate finally the stress intensity factors. So again, A and P, here again, this A shouldn't be transposed. We have the unknown coefficients and the polynomial basis. We minimize again this discrete weighted L2 norm J with respect to A. Of course, now our approximation has changed. It's not only anymore P transpose A. We have added that term here, minus these nodal parameters. So we have here the standard nodal parameters plus 2 more, but actually 2 more is only when you have 1 crack tip. When you have like more crack tips, then you have correspondingly more. So NC is the number of crack tips. So we can go now through the same procedure. We take the derivative with respect to A, solve this equation with respect to A, and plug it back into the original approximation. And what we finally obtain is then an approximation that looks like this one here below, where we have here the additional parameters K1 and K2, and U tilde is basically that expression. So probably the most common way is the so-called extrinsic partition of unity enrichment. So what is shown here is actually a so-called global partition of unity. So we have here sum of the shape functions times the nodal parameters. And what you can do, you can add here now additional parameters. So we have here sum over k equal SC. So basically it's k is equal from 1 to 4 because we have 4 functions stored in this vector P. And B are additionally degrees of freedom that we introduce into the variational formulation and that we have also to solve for. So what do we do in a local partition of unity enrichment? We would simply split the second part. So we have here sum j element S, phi j times uj, plus, and then we have another sum. Unfortunately, it's not shown here. We have sum of j element SC, phi j times that term here. So SC would be the set of nodes in front of the crack tip. So we have only additional degrees of freedom for a selected number of nodes in front of the crack tip. That will actually cause also difficulties due to blending. I don't know, maybe some of you are familiar with XFEM, so that issue is also present in meshless methods. And that actually was also proposed in the paper in 1997. So I would like to show also some results of this enriched meshless methods. Here again, let's say for a mixed mode problem. So we have here the error in the energy norm versus distance of the particles. For the visibility, diffraction, and transparency methods, here again we have a convergence rate of 1/2. If we add now an enrichment, extrinsic PU enrichment, PU means partition of unity, intrinsic partition of unity enrichment, extrinsic MLS enrichment, you can see we can first of all get a much more accurate result, and secondly we get also a better convergence rate. So of course the convergence rate needs to be in the asymptotic range. It's only between the last 2 points, and the optimal convergence rate is not achieved. As you can see here, it's supposed to be 1 for a linear EFG approximation, and actually at that time the simulations were actually done by one of my collaborators, Dr. Fu. So we didn't use, for example, special integration techniques. We just added then a lot of quadrature points. We also didn't do anything about blending, and that's the reason why we didn't get here optimal convergence rates. That is the normalized stress intensity factor for the visibility, diffraction, and transparency method. Now for the stress intensity factor K1, and here for K2. So you can see the error is actually quite large. Here for a coarse mesh, 60%. It goes down then, for example, at this point to less than 10%. So if we use an enrichment, I'm actually not so sure. I was also a little bit suspicious when I saw the results that it's the coarsest mesh and they have an error less than 1%, which looks to me a bit too good, but maybe also the enriched domain is in the order of the entire discretization domain, and then I think these things can happen. But you can clearly see the improvements quite drastically by adding this enrichment. So, and of course that is here the same for the stress intensity factor K2. Here the results are not as good, but I think still we have errors in which are then less than 1%. As I said, it's also not really like the method that I developed. It is like a method developed in 1997. Okay, I have to open now the next slides. Or are there any questions? Okay, I want to come now to the next part, to partition of unity enriched methods. So I will focus on the extended finite element method. I don't know, is somebody working here on XFEM or using XFEM? Nobody? Okay, yeah, but I will explain a little bit XFEM, actually quite the basics, and also not too much details. I give actually a course in my university and also one in Vietnam, which is called Extended Finite Element and Meshless Methods. But the course, the number is like 775 hours altogether, the lecture. So I try to condense it down here now in like 2.5 hours. I would like to explain then what is XFEM, the basic idea, how to implement it. I want to come to the so-called smoothed extended finite element methods to show you like an alternative related to how to integrate the singularity. Then the Hansbo XFEM, so that was proposed actually in 2004 by the brothers Hansbo from Sweden. It's actually a very nice idea, and that version is actually implemented in Abacus. I think Abacus has two versions. One is a so-called standard XFEM with a full tip enrichment. And I have not looked into Abacus for a long time, and actually usually ask my student to do it, but if I remember correctly, this full enriched XFEM formulation cannot deal with crack propagation, and you need like an external tool. And a colleague of mine, Marc Duflo, he has actually developed such a tool. But the Hansbo XFEM method, even like some time ago, could deal with a arbitrary number of cracks, of course combined with cohesive elements. And the reason for that is probably because it's much easier to implement. When Hansbo and Hansbo published that paper in 2004, my mentor at that time, Ted Polichko, he looked at it and he said, that's standard XFEM. So he first wrote in another letter, and I'll show it a little bit later as well. If you look only at the kinematics, you can show a Hansbo XFEM. It's exactly the same as a extended finite element with a so-called shifted heaviside enrichment, so without a crack tip enrichment. And a little bit later, they came up with a method which they called phantom node method. And actually afterwards, there was also another paper by Steinmann, Alan Kuhl, and Julia Merkheim. They have actually a phantom node method in statics, but unfortunately, they didn't give their method a name. And I think that's why the method is a little bit less popular. So I think sometimes a good name is also important for the advertisement of a computational method. And I want to show you also some of the works of extended meshfree methods, particularly methods that can deal with a large number of cracks. Okay, before I start with the extended finite element method, I would like to explain a level set method. Often when you hear XFEM, it's related to level sets, though it's actually not really necessary to use a level set methods in XFEM. So why do we use a level set method, or where does it come from? I think the key application is fluid mechanics, where you represent a surface implicitly and then you solve a Hamilton-Jacobi equation to propagate the interface. And the interface propagates usually orthogonal to the interface. And cracks are quite different. I come back to that a little bit later. So let's assume we have here domain omega. We have domain omega A, and we have maybe an inclusion. We have then domain omega B, and we have then here a level set. And assume we have now a circular domain omega B, where the center of the circle is in the origin. Then we can, of course, write down a function of the level set, x squared plus y squared minus r squared is equal to 0, where r is the radius of the circle. So that is apparently the original position of the level set. If we plug then now, for example, we have here discretization, you put in now the positions of the Gauss points or the position of the nodes in the domain omega B, you will find that the level set function in omega B is smaller than 0, and the level set function outside the domain is larger than 0. So the level set function can nicely and elegantly define in which domain you are, or in which domain is a certain point located, either in omega A, in omega B, or on the interface. The level set function has also another relatively nice feature. When you would like to compute the normal at any point to that interface, you can simply take the derivatives of the level set function, assuming that here the Euclidean normal is equal to 1, and then you have the normal, which is supposed to be a unit vector. And in case you would like to compute the curvature, that is simply the derivative of the normal and the second derivative of the level set function. So that is not so useful maybe in fracture, but maybe in fluid mechanics. So let's look here at, we would like to integrate now a function g, or the actually derivative of a function. Let's assume we have here now like domain omega a domain omega b, and that is here the normal, that is here an interior interface. So that could be, for example, a crack that crosses now the two domains, or separates these two domains. Then we are interested now in computing the integral of a derivative of a function in the domain omega a, and we can rewrite that by using the so-called Heaviside function. So we have the Heaviside function, which is equal to 1 when f of x is larger than 0. That would be actually this domain. And in domain omega b, the level set function is supposed to be equal, where f is smaller than 0, then the Heaviside function is equal to 0. So we can look here now at that term, g comma I, that is the derivative of g with respect to xi times h. We can first use partial integration and then the Gauss divergence theorem. So that is done here, partial integration. So we have g h comma I minus that term here, where we have here the derivative now of the Heaviside function. So the derivative of the Heaviside function is Dirac delta function, and the derivative of f is equal to the normal. So that term is simply the normal. That is here actually the internal normal, that what you see here on the picture, and that is here the outer normal. That can be shown here then in a little moment here as well. So that is basically here g and I. That is basically here it's an interior boundary, and when I transform this here now into the domain integral into a boundary integral, and here I've made another mistake. Here it should not be omega, it should be gamma. So we have g times h times n external. That would be the external boundary. So of course you need to be also careful with the normal. When the sign of the normal changes, and the direction changes apparently as well. So one very useful level set function is the sign distant function, and that is particularly useful for the enrichment scheme. Remember, you need to we would like to compute theta and r. So for example, if you have a crack tip, well, I don't have here now a picture, but let's assume the crack tip would be somewhere here. You can have the extension of the crack tip. You have here a point here. Then that would be the distance to the crack tip r, and then here the angle theta would be the angle between this extension of the line and the line that connects the material point to the crack tip. And these functions can be nicely expressed in terms of the level set function. So that is the advantage of using level set functions in the extended finite element method applied to fracture. So a special level set function is a sign distant function, and here's also a mistake in the figure. So actually in the equation, so that is here x gamma c. That's a point on the interface, and that is a point xi. So actually, usually one would define x gamma c minus xi, so that points here in the direction, and that would be then plus d and not minus d. So that is then in domain omega a, and in omega d that points actually in the opposite direction. You have then the minus d. So here that is again the sign distant function. That's the minimum distance from a point to the interface multiplied by the sign. So here again n is a normal. So if the scalar product between n and x minus x tilde is larger than 0, that means it points in the same direction. Then it's equal, then it's larger than 1, and it's a positive sign. If it points n is this direction and xi is on the opposite side, then it has a negative value, and we have negative sign, and we have minus d. So what one would usually do in an extended finite element method, one would discretize also the level set function, either with the same shape function as our mechanical field, like as our displacement field that is illustrated here, or one can have a completely different approximation of the level set. For example, a finite difference approximation that was proposed by Combescure some time ago, I think around 2005, or just a finer mesh. That is also possible. But then, of course, you just need to have the nodal parameters of the level set functions in order to figure out if you are on one side of the crack or the other. Having said that, of course, here's a key difference between fracture simulation and, for example, a fluid flow simulation. So what one would do in fluid flow simulation, you would simply solve this Hamilton-Jacobi equation. So we have here the material time derivatives of the level set function f with respect to t. You actually know the velocity of the interface in fluid mechanics, and you would solve this equation with respect to f. It's a hyperbolic differential equation, so one requires actually an upwind scheme. I have just shown here like a forward Euler, which is not necessarily stable, but one would solve this equation with respect to the level set function. Of course, in cracks it's quite different, because v could be then here the crack speed, and the crack speed apparently is usually not known. So this equation is not so useful. In fracture we have usually a cracking criterion, and then we put usually in front of an existing crack segment when you control the crack length. Though I will later show you also like a similar equation where you could theoretically use a similar equation to determine the new position of the crack tip. Okay, here again, what is the principal idea of the extended finite element method? So we have here the standard approximation. So U are our Uj are the standard nodal parameters. Phi are the finite element shape functions, plus an enrichment. So we have here phi. That is an enrichment function, which we choose according to our analytical solution. And most importantly, often it's not really necessary to have an exact idea about the analytical solution. So for example, if you are dealing with shear bands, or if you have like nonlinear material behavior, then you don't know exactly the enrichment function, but we, for example, know for a shear band that we have a canonical velocity distribution orthogonal to the shear band that follows an equation like tangents of hyperbolicus, or we know that a crack is a jump in the displacement field, so that a step enrichment can be used to capture this discontinuous displacement field, though we might not know exactly what is the size of the jump. We add in here additional degrees of freedom A, and we have to solve for this additional degrees of freedom A as well. Plus we might have here additional degrees of freedom. Maybe another example is like if you have an interface problem. So you know that you have a discontinuity in the strain field. So you could choose now an enrichment function that has a kink at the interface, like synapse enrichment. It's an absolute value of the sign distant function. So that will also cause a jump in the strain field. Actually, man has also shown that you could choose here now different shape functions for the enrichment. So here, most importantly, I would like to point it out, that is here, S are the set of all the nodes in the discretization, while S enriched are only a subset of the nodes S. So for example, if you look here at the figure here below, well, of course, here I didn't really show all the enriched nodes, and it's actually also a meshless discretization. But for example, if you look here at this red node that is affected, or the domain of influence is affected by the crack, so that is a node that needs to be enriched. It needs to be enriched, for example, with a step function, because the entire domain of influence is crossed by the crack. While this black node, the domain of influence is only partially cut by the crack. So here you would like to use a crack tip enrichment, like the square root r sine theta over 2 terms. Okay, and here this phi tilde could be also a different shape function to phi. That just needs to fill partition of unity, sum of the shape function equal to 1. So theoretically, one could use here a quadratic approximation, and here only a linear approximation. But of course, that's not very popular. And if you want to deal with several cracks, then you simply sum over the number of cracks. So if you have like more cracks, then you have to add additional degrees of freedom. So for example, if you have now another crack, for example, here in the upper domain, then this node has not only the standard degree of freedom, it has the enriched degree of freedom for crack number 1, it has the enriched degree of freedom for crack number 2. And you can see, like, if you have complex crack patterns, that can be quite challenging if you have to implement that. The crack interaction, of course, is still another issue, but a little bit later I come also to some of the limitations of the extended finite element method. So here let's look at application of XFEM, and I would like to show XFEM on an element level. So how do how does the element stiffness matrix look like? I have here now two applications. One is a bimaterial. So we have a material that crosses an element, and we would like to account for that. We would, of course, we can mesh that out. We can align the boundary of the material to the element, but here we would like that the bimaterial crosses arbitrarily an element. That is useful when the microstructure is quite complicated. So the displacement field for a bimaterial is apparently continuous, while the strain field is discontinuous, and then we can use here this UPS function, or sometimes called ramp function, that is the absolute value of the signed distance, and psi, if I go back, psi is here the enrichment function. That's a function we have to somehow choose according to our the knowledge of our analytical or of our solution. So if we have a crack, of course, the displacement field is discontinuous, the strain is not defined, and then we could use a function that is discontinuous. You can use any discontinuous function. So for example, you can use the step function, which is +1 on one side of the crack and -1 on the other side of the crack. Or you can use the Heaviside function that jumps from 1 to 0. So I would like to explain the extended finite element method for a relatively simple example in 1D, and I hope one can see actually the shape function I would like to show here. So let's assume we have three elements, element 1, 2, and 3. So that is here the element that contains a crack at this position. So at this position we have a crack. Here these two elements are the so-called blending elements. These are the neighboring elements to the cracked elements. And you can see that is here now the approximation. So we have here sum of the shape functions times the nodal parameters, and that's the enrichment. And that is given here, for example, for the first element that shows here, that's the shape function, this head function for node number 1. This is here the shape function of node number 2. That would be f equal to 0. On this area we have f smaller than 0. On that side we have f larger than 0. So we have, when we use, for example, a step function, this step function will be equal to +1 on that side, on the right side. And on the left side, my step function s will be -1. So, and now we can illustrate the so-called enriched shape function. That is the product of the enrichment function plus the standard finite element shape functions for these two nodes. Of course, that's only the interpolation in that cracked elements. And we have here the shape function of the element here. That's, I think, pretty obvious, because we simply multiply now these shape functions by -1 on the left-hand side and by +1 on the right-hand side, and then we obtain here such a shape function. And if we look now at the enriched shape function, s times n of node number 2, then we obtain such a shape function. Here we have a value of +, of course. Here we have a value of -. And if we would like to compute now the jump on the displacement field, I'm going to show that a little bit later, more detailed, when I come to the Hansbo XFEM. You can see, of course, the first approximation is continuous. That can be clearly seen also from the shape function itself. So this term cannot create a jump in the displacement field. But if you would like to compute now the jump in the displacement field, you would interpolate with the nodal parameters from the left and from the right-hand side when the point reaches the crack. So, and if you have a step function that jumps from +1 to -1, you can actually show that you have here a factor of 2. If you replace now the step function with the Heaviside function, then this factor of 2 will vanish and you have only a factor of 1, because jumps only from 0 directly to 1. One drawback of this this enrichment is that you lose the interpolation character of the finite element method. So, and here's another error in the equation. So, for example, let's look at this node. Let's assume k is now node number 2. That is node number 1. Node number 2. Then we can compute now the displacement of node number 1 simply by this interpolation. So it's pretty obvious. The shape function of node 2 at the position of 1 is equal to 0. That is basically shown here. And of course, that's also the case for the enriched shape function. So the value here is equal to 0. So when we interpolate, we can actually say u of the position x2 is equal to the parameter u at this position. Yeah, that is basically simply u2. But now we have here the enrichment. You can see that here. We have also an additional degree a, and that should be ak and not aj. So we have here now the value of ak that we solve for in our system of equations, plus the value of the step function at f of xk, and that is equal to +1. So our interpolation, or our true displacement field is actually uk plus ak. So it's not anymore uk. So in other words, when we obtain now the nodal parameters uk and ak, of course for the entire discretization, then similar as in meshless methods, we need to still to interpolate if we would like to obtain the physical value of the node at this position. However, there's a way out of it. As at least it can be done fairly easily for an enrichment function which is constant. One can use a so-called shifting. Of course, you can choose arbitrary enrichment functions. So instead of using s of x, you use a shifted enriched function, which is s of x minus s of f of xi. Yeah, that is basically shown here. Or here is sum over j, s of phi of xj. So what does it mean? We look only now at the second part. So we have here the shape function ni times s of phi. So if I look, for example, at this node, then for this node, the step function is going to be positive. And now I subtract a sum now over the nodes j. So s of phi of x2, that is basically this function minus this function. So on the right-hand side, we have now removed the this value is equal to 0, and that means the entire term here is equal to 0. While when I look now at the left-hand side, again, I look here now at node number 2, and at node number 2, the value of the step function is equal to +1, but the value of the step function of the neighboring node on the left-hand side is equal to -1. So I have here 1 minus -1, and that is 2. So with this so-called shifting, I have now reconstructed my shifted step enrichment, and this step enrichment looks like that. So you can first of all see it's much narrower. We don't have the term here on the right-hand side. And you can also see that at this point here, the shape function is equal to 0. So the first nice effect is u at the position xk is indeed equal to uk. And second, you don't have problems with so-called blending. Blending elements are elements that have not only enriched degrees of freedom, but also standard degrees of freedom, like this element here. Here you have an enriched degree of freedom and a standard degree of freedom. And here you have only the standard degree of freedom, but you lack the enriched degree of freedom. And that causes problems and finally will deteriorate the convergence rate. So what you can also do, you simply use a Heaviside enrichment. So the Heaviside enrichment is 1 on one side and 0 on the other side. Of course, the figures look quite similar. So I've shown here that's a standard degree of freedom for this first node. That is the standard shape function of the second node. So that would be then the shape function, the enriched shape function of that node here, because on this side the Heaviside function is equal to 0. That would be the shape function of the second node. We still have, of course, the same problem as with the step function. So we can use here again a shifting, which is, for example, shown here for node number 2. And then we have here this shape function. But of course, instead of having here now for the enrichment here, a jump where we have a factor of 2, we have only a factor of 1. So again, what is the problem with the blending? So here that shows like a crack or like an interface. In gray you can see the enriched elements or the omega partition of unity. In this case, so-called partition of unity is fulfilled, means sum of the shape function is equal to 1. You can clearly see that when we look here, the sum of the shape function is equal to 1. For the second term, also sum of the shape function is equal to 1. For the element here in the middle, you can see we have that's the shape function, plus this shape function. However, if we look here at the neighboring element, we don't have an enrichment at that node, so that is the shape function for the second term, and it does not full partition of unity. And that causes also difficulties. So this is like here, this shaded area, the so-called partial enriched or area, or the so-called blending elements. They have, and not only all, so they have here some nodes which are enriched, but some nodes which are not enriched. So for example, if you would like to reproduce now our enrichment function psi, actually that is not that relevant, because the enrichment function psi does not lie in the blending elements, but only in the enriched elements. But nevertheless, you cannot reproduce this this function in the neighboring elements, because some of the shape function in the blending elements for the enriched part is unequal to 1. And there are actually a lot of papers that show that because of this blending combined with integration, the optimal convergence rate in XFEM cannot be recovered. So if you, for example, would now just implement the XFEM without any additional techniques for blending, without looking into details for integration, and without looking how you enrich the elements in front of the crack tip, you will not obtain optimal convergence rates. Okay, I come back to that a little bit later, but I would like to explain now the extended finite element on an element level. So, of course, first we start with a given element. So, for example, the Q4 element, which is one of the standard or very popular elements in finite elements. So we use an isoparametric mapping. We define here a parameter space where we define the shape functions. So, for example, that is here node number 1 here, node number 2, node number 3, node number 4. We have this classical Lagrange polynomials where we define the shape functions. And then we have the mapping from the parameter space into the physical space. We look now at our approximation. So we have the usual displacement plus the enriched one. Maybe let me go back a little bit. So that portion that is often called the standard, U standard plus U enriched, or U continuous plus U discontinuous. And sometimes when you look at multi-scale methods, they say we have a fine scale and a coarse scale, so that they compose a displacement field into a fine scale and a coarse scale part, or in this case into a continuous part and into a discontinuous part. And here we can, of course, write down now or store the shape functions also in a vector matrix form. So we have Ux and Uy. This is a displacement in x and y direction in 2D. So n is the usual. It's a matrix that contains the standard shape functions, and n enriched are the shape functions that contain the enriched shape functions. So for Q4 element, what is the size of n, the matrix? What is the size? Somebody knows? So you have 4 elements. How many degrees of freedom? 2 per element. So what's the size of the stiffness matrix? 8 times 8. So you have here a 2 times 8 matrix. Here with the enrichment you have another 2 times 8 matrix. So you have here an 8 times 1 vector, here another 8 times 1 vector. So finally you have here, when you look at the entire matrix that contains the shape functions, you have here a 2 times 16 matrix, and here the degrees of freedom 16 times 2. Of course here for this very specific problem. So when I go back here, we have not only the standard degree of freedom U1 and U2, we have also now the degree of freedom A1 and A2, which are related to that term here. So we have now these degrees of freedom plus those degrees of freedom. And if you have a crack tip, then you would have, like I've shown before, you have then an additional 4 degrees of freedom per node, so you have then correspondingly more. Of course, usually you don't have an enrichment for the heavy side and simultaneously an enrichment for the crack tip. You have either one of them. Though that's also not mandatory. So here again, that's n usual of actually it's also not ni. So that's of course related to all the nodes. Yeah. So we have that is n1, n2, n3, and 4 of this for the shape function of each node in the, for example, x direction. This is the shape functions in the y direction. But actually, that's not the shape function in the y direction, but that's the interpolation related to the nodal parameters. So the first line is the nodal parameters related to the x direction, and that is related to the y direction. And then we, of course, have the enriched shape functions. So we have here n tilde. So what is n tilde? That, of course, depends a bit on what problem we solve. So, for example, if we have first of all, I would like to mention we have a shifted enrichment. So we have psi I of xi. That is simply a shorter abbreviation of psi of x minus psi of xi. So if I go back again, let me go here. That's exactly what I've, okay, let me go back again. That's what I've done here. Psi f of x minus psi f of xi. Unfortunately, I have not really used the consistent notation, but that is exactly the shifted enrichment. Okay. So one could use here a shifted enrichment, which makes sense when you have a crack. So if psi is equal to the step enrichment, and if you have an ups enrichment, you can of course also shift the enrichment, but you will not get rid of the blending, because you multiply a shape function which might be bilinear with a function which is linear, and that cannot compensate the error, because the standard enrichment is also only bilinear. So here we have the standard nodal, the vectors with standard degrees of freedom, ux1, x2, x3, x4. So the first index refers to the direction, and the second index is the number of the node, and of course here related to the y direction, each node, and then the additional degrees of freedom related to the enrichment. One second. Okay, I'm sorry. This could feel my voice is getting a little bit rough. Okay, so let's look here again at approximation, particularly the second term. Of course, what we finally need, we need also the gradient of the displacement field. So we simply have, these are of course nodal parameters, ui and aj, so we don't take derivative with respect to them, we just have the derivatives of the shape function, and here the derivatives of the enriched shape functions, n times psi. So we have then here the derivatives of the shape function times psi plus n times the derivatives of the enrichment function psi itself. And of course now it depends what you plug in here for psi. In case you, that was also relatively quick. In case you have here this the sign enrichment, so the absolute value, so we have simply the sign of the level set function times the derivatives of the level set function. That's the classical ups enrichment, what you would use for modeling a material interface. And if you would have a crack, you would have here the heavy side or the step function. And what's the derivative of the step function? The Dirac delta function. So that term is simply not present anymore when you have a step enrichment, and you simply have to multiply your shape function with a step enrichment, which is accomplished quite easily. So then we of course need to compute the derivatives of the shape function stored in the B matrix. Of course, finally we enter B transpose CB, that is stiffness matrix on an element level. So D is our differential operator in 2D, N is our usual matrix. So if that is here 2 times 8 matrix, that is here 3 times 2 matrix, then our B is a 3 times 8 matrix. We have a 3 times 8 matrix for the standard part and a 3 times 8 matrix for the enrichment, which is shown here. So that's here the usual part. That is here the enriched part, and of course we have here, of course, the vectors containing the nodal parameters, the degrees of freedom per node. So here again, we have the enriched part. So we have the derivatives of the enriched shape function. So that is n, I times psi. and psi comma I is equal to the sine f of x and f comma of I. So that is here for the UPS enrichment for material interface, and that term is equal or vanishes if we have a crack. And for the crack we have only the first term where psi I is a shifted step enrichment or the shifted heaviside enrichment. So what one also needs to do, one needs to, this one is not necessary, but one often discretizes the level set function. So we have the nodal parameters of the level set, and then we discretize it, and in case we would like to compute the normal, we can compute also the derivatives of the level set function. And here taking the derivatives of the nodal parameters, and then later we can use the level set function to approximate R and theta in the tip enrichment. It's not so useful if you have only a step enrichment. So when you have a step enrichment, your physical criterion usually tells you the orientation of the normal, and then you just need one point of the crack on the crack surface or on the crack line in 2D. And often one also assumes that the crack has to cross the entire element if you use only a shifted step enrichment or a standard step enrichment. So finally, what can actually show you end up with a system KD equal to F. So of course what you do, you have the standard variational form, and you have a discretization of the test function and the trial function, plug it into your variational form, and then you end up with a system which is also KD equal to F. But of course you have here the standard. Let me just, okay, now I don't have a board to write something, but now I need to go a little bit back again. Need to go to the formulation of the enrichment. Okay, so you have actually here, that is the displacement field, or the so-called trial function, n times u plus n enriched times a. That's a trial function. So you have, of course, the same approximation for the test function. So you would have here delta u, which is n times delta u plus h n times delta a. And that is what you plug in finally into the weak form. And then you get these terms where you multiply cross-multiply the test functions. You have basically the parameters u times delta u. It's like standard times standard. Then you have delta u times a, that is standard part of the test functions times the enriched part of the trial functions. And then you have delta a, the enriched part of the test functions, times u, the standard part of the trial functions. This is the so-called mixed terms. And of course you have multiply also the standard as the test function and the trial functions of the enrichment. And if you do so, you obtain finally a stiffness matrix which looks like this here. 1 second. K standard, that is related delta u times u. K standard enriched, that is delta u times a. K enriched standard delta a times u, and K enriched delta a times a. Yeah? So correspondingly looks also your the submatrices of your stiffness matrix. So you have B standard transpose C B standard. That is what's every finite element is a standard Q4 element that is up in the upper corner here. So the size here is an 8 times 8 matrix. Then you have K standard enriched, that is B standard transpose, which is related to the test function of the standard, times B enriched of the trial function. That is up here in the upper part. That is the first mixed term. And then you have here delta U A. That is here B enriched transpose. That is related to the test function of the enrichment, and B standard, the trial function of the standard part. And of course, K standard enriched is equal to K enriched standard transpose. And then of course we have here this enriched part, B enriched transpose C B enriched, and all of this is going to be a 16 times 16 stiffness matrix. So the rest is, I think, pretty standard. We have here we take the derivatives of the shape function or of the enriched shape function delta n times x. So we have here formulated n in a parameter space. So we have derivative of n with respect to xi, and then the xi dx, that is the inverse of the Jacobian. That's what I meant when I say that term here contains only, this was my comment for the integration, where I say we actually do not integrate a polynomial function. We have also a rational function FEM because of that term. It's only contains constant parts if we have a linear triangle, but already for a Q4 element with the bilinear shape functions, that term is not constant anymore. Or this matrix does not contain constant terms anymore. So we can write it out here. Of course, we have here the chain rule. For example, derivative of shape function of node I with respect to x. We first take derivative with respect to r, the r dx, and plus the derivative of the shape function with respect to s. That is the other direction, the parameter space, the s dx, and that, of course, are the components of our Jacobian, or in this case, of course, the inverse. So the only thing what is remaining is we take the derivative of the shape function, which is also quite standard here. So how to compute the Jacobian? I think everybody knows that as well. Of course, that is in an isoparametric concept. That means we have the same shape function to discretize our geometry as our trial functions, our displacement field. So we discretize our geometry also with Q4 shape functions. Xi are the position of the node in the global parameter space, and then we can simply take derivatives of x with respect to r and s, and this, of course, are the components of the Jacobian. So how do we integrate actually in XFEM? So if we have no crack, it's fairly simple. We use standard Gauss quadrature. So one can show when you have a standard Q4 element, we need in two direction 2 Gauss points. That's the minimum number of Gauss points we need to integrate. It does not make sense to use actually more. However, when we have here a crack, we cannot integrate across the crack because we have here discontinuity. So most popular is a sub-triangulation. So what one would do is we have here a crack. You use a Delaunay triangulation in an element. And of course, you need to be careful that you not accidentally have a triangulation across the crack. So we need actually a constraint Delaunay triangulation because otherwise you integrate still over the crack, which you do not want. So then you integrate here in the upper part. So we have actually now two mappings, and now you can see an equation where we have another mistake. So we have to integrate a function f first in the domain omega minus and then in the domain omega plus. That's integration in the physical space. So we first have a parameter space, so that should be like omega tilde or so. The parameter space is then defined here in the lower part and also in the upper part. That parameter space is again triangulated. So here we have then another parameter space which depends on the coordinates eta. And then we map first from the triangular parameter space in the other parameter space, and then back into the physical space. So it's actually quite simple. We just need to compute now these two Jacobians. I also would like to point out we do not introduce here another node. We just need that here for integration. Of course, we have only these 4 nodes. Okay, what might be an issue when you, for example, have a crack which is slightly curved. If you want like to have like a relatively coarse discretization. If you, for example, use now your level set to approximate the crack. So let's assume we have actually a triangular element, and you approximate now a curved crack with a triangular element with a linear shape function. That means your element does not see the crack as a curved crack. It sees the crack straight, because the triangular element can only reproduce a linear function, but not a bilinear or not a quadratic function. So what one can do to improve the accuracy, if you would like to keep a curved crack in an element, that is, for example, the case if you have now crack propagation. So, for example, you have here a slight king, so the crack tip in the first propagation step ends up here, and then it propagates further to the next element. You're going to have a kink in there. So what you would like to have is maybe a triangulation that looks a little bit like this, where you also make sure that the integration points after the sub-triangulation lie on the correct side of the of the element. So for example, if you look here, element number 3, I think it doesn't look so bad, but if the crack would be more curved, then maybe you have an integration point which lies on the opposite side of the crack, and that of course introduces integration errors. Another way to integrate is, it was also proposed by, I think, Combescure some time ago, is why not using just a large number of quadrature points. So for example, assume you have now a nonlinear material and you propagate now the crack into that element. So apparently what you need to do, you need to map the variables from one Gauss point to another, and that can cause errors, and it particularly will cause errors very close to the crack tip. So if you just use a large number of integration points, you can, for example, define a certain area in front of your crack tip, which has more integration points. You cannot avoid the mapping, but you can do the mapping earlier. That means before the crack is close to your crack tip. So you introduce the error a little bit earlier, actually. What you can do as well is you can modify the quadrature weights. I've done it first in Meshless method, and I've seen actually a little bit later that they have used that also in XFEM. So the basic idea is you generate here again a Voronoi diagram here in that element that will lead you to the Voronoi diagram that you see on the right hand side, and then you would modify now the quadrature weights which are affected by the crack. That would be here these two quadrature points. Apparently the quadrature points above are not affected by the crack. Having said that, of course, what you need to know is you need to know the position of the crack in the parameter space. And of course here I assume also the crack crosses the entire element. So what do you do then? You simply modify the quadrature weight. So I have here a quadrature weight omega minus, which is a standard quadrature weight, but related to the area here below the crack. So that is Vi minus, that is the area below the crack. The total volume or the total area in 2D would be V. And I have a quadrature weight Wi plus, which is related here to the upper part. So that is another way how to integrate. Here I have discussed only how to integrate the step enrichment. I have not said anything about the tip enrichment. In fact, I have not even shown you the discretization for tip enrichment. And in fact, I have not included it in the presentation because I don't have enough time. But I also would like to mention other integration schemes which were done by Thomas Fries. So he has introduced here special elements only for the integration. So I would like to emphasize that he does not modify the finite element approximation anymore, but he introduces now an element to integrate certain portions a little bit more detailed. So for example, let's assume we have here that interface, could be also, of course, a crack. And then you can see we have a triangular element here. So we can, for example, have here now, for the integration, we have here one node, and on the other side we have 4 nodes. Yeah? Or we have the other elements that is also shown here, if the interface is on the other side. And then, of course, we have the upper part. So we have here a linear interpolation along these 3 sides, and there we could have, for example, a cubic interpolation. So if you, for example, have a plate with a hole problem, one key issue is that, of course, when you have the hole, you cannot capture the geometry of the hole very nicely with linear finite element shape functions. In fact, if you even use a quadratic, or in this case a cubic shape functions, you will not capture the hole exactly neither, but at least you are much closer to that, and then you can have now special integration techniques which accounts for the curvature of that hole. Maybe here just also a side comment. If you look at an extended isogeometric analysis shape function, for example, based on non-uniform rational B-splines, they can capture the shape of a circular hole exactly. And they are therefore, I think, better suited than Lagrange polynomials for this specific application. Okay, also some details. What theoretically can also happen in the course of a simulation, let's say when the crack propagates, that of course is the extreme case. The crack could directly go through the nodes A and B. It would coincide with one of the element edges. So the enrichment for that case will be a little bit difficult. And if you, for example, look at your sub-triangulation, that would be the, maybe it should, for example, when you have now, let me see, you look at this crack here. What you do here is maybe well, let me go on back. Okay, let's say you have here the crack. You do a sub-triangulation below. The sub-triangulation will not be that easy if the crack is now exactly on that node, at least below the below that part. So that is, I think, not possible. Of course, when you look at it, it's quite simple, but you need to tell it also to your code. You need to say, okay, when the crack is now too close to some of the nodes, then please do not sub-triangulate below it. Please do not enrich certain nodes. And one can, for example, look at a node and the element patch around the nodes. So that is also quite easy to get because we have the connectivity areas. We always know to which to which node belongs a certain element and vice versa. So for example, for that node, we know it's attached to these 4 elements. And then we can compute now the area of the elements which are above the crack. So for example, that is here now the crack segment. The crack segment has, if it's a straight crack here, normal. Of course, the points here, so we know definitely on what side of the crack a node is, and also a Gauss point. Then we can compute the area above the crack of the patch of nodes. We can compute the area below of this node patch. And then we can compute the ratio, A omega below and A omega above, divided by the total area of this patch of elements. So when the ratio is either very large or very small, for example, if it's close to 1, 0.999, or if it's close to 0, then you would not enrich the corresponding node. So what would that mean actually? Okay, I didn't show it here, but let's for example, if you look here now at such an enrichment, you can clearly see, if you look now at, for example, node number A, the ratio is not so bad. You would enrich the node, but for example, for node number D, the ratio would be extremely large. If you look at the patch above, so you would not enrich node number D and node number C for this case. You only enrich node number A and node number B. I already mentioned relatively briefly, it is important that you account for blending. It is important that you integrate properly. I have not looked at the tip integration. I come back to that a little bit later when I come to the so-called smooth extended finite element method. And it's also important how you enrich the elements. So in the first XFEM papers, they use the so-called topological enrichment. So you can see here that's supposed to be the crack. So the red nodes are the nodes associated to the step enrichment or to the heaviside enrichment. And then you have an element that contains the crack tip. So that element would be enriched with the crack tip enrichment, which is termed square root of r sine theta over 2, and so on and so forth. So if you enrich only the element where the crack tip is contained, that is a so-called topological enrichment. And I think you can clearly see what we have to show in a finite element discretization when you refine the mesh, that you get better and better results. However, if you refine the mesh and you only enrich the elements which contain the crack tip, then of course the enriched area gets smaller and smaller and smaller, and in fact you will not get optimal convergence rate. That was also shown, I think sometimes in 2000 by Béchet and some other co-workers. And they recommended a so-called geometric enrichment. That means a little bit similar to what I've shown in the meshless approximation. You simply draw a circle around the crack tip and say, okay, in that circle, however size it should be apparently sufficient large, we enrich all these nodes, And of course, when you refine the mesh, then in this geometric enrichment, it's completely not affected in terms of the enrichment area. However, what of course is an issue, when you refine the mesh, then you have a lot of elements which contain this crack tip enrichment, and that destroys the bandwidth of your system matrix. It deteriorates the condition number, and you need to have some special techniques to deal with this ill-conditioned system. So you gain something and you lose something. There's always the saying, no lunch comes for free. So though this can recover optimal convergence rate, I think in most applications one does not use a geometrical enrichment because it's simply relatively cumbersome to make sure that your system of equations is well conditioned. I would also like to point out some other limitations of XFEM. So of course XFEM can deal with arbitrary crack growth without remeshing. However, it still needs some interaction between the crack and the underlying discretization. So for example, let's assume we have here this given discretization and we would like to model a crack like that. And assume we don't have a tip enrichment, only a step enrichment. That is actually not possible because what would it mean? We have, if we enrich now all these 4 nodes, that would mean the elements can open along this edge and it will open along that edge and the crack tip will close here. So that is the classical edge crack problem. If you would like to have the crack close at a certain edge, you cannot enrich these nodes. And that actually means in this case you will not enrich any nodes and there's no crack. So what you need to do at least is, unfortunately, let me see if I have I don't have the figure in here now. But okay, let me just if you, for example, would like that the crack opens like here and closes like this. Yeah, so we have here a crack opening. Then you would enrich these 2 nodes. You will not enrich the nodes at that edge. Not having here additional degrees of freedom means they cannot open because there's no enrichment that compensates for the crack opening. So only along that line where you have additional degrees of freedom, you can have the crack open, but not here. If you, for example, have now a tip enrichment, then you would have an interaction between these 2 crack tips. So you would, for example, have an enrichment for this crack tip in one element, and you would have an enrichment for that crack tip in one element. And there are actually some numerical trials to do so, and the results are actually extremely poor. So what you need to do, you need to at least expand the crack so that we have in one element one set of crack tip enrichments, and in the other element a new set of crack tip enrichments. Having said that, if you, for example, have now a crack approaching with a different crack tip enrichment, so how accurate that's going to be when the cracks interact is still, I think, an open question. I think theoretically, of course, from an implementation point of view, it's possible. How accurate the results are is, of course, a separate issue. Okay, let me see what's the time. It's already 4 o'clock. Maybe we should have like 5 or 10 minutes break, and then I continue with smoothed XFEM, Hanspo XFEM, and then some alternative methods.